Hello everyone, my name is Pouya and I'm presenting to you our paper with Liubov and Hoormazd from Stanford University titled Airbnb Price Prediction Using Machine Learning and Sentiment Analysis. So let me start with an introduction. The problem we've looked at here is that pricing a rental property is challenging for both the owner and then evaluating the proposed prices are challenging for the tenants. So what we have tried to do in this paper is to create a predictive model to predict the price of Airbnb listings using property specifications, owner information, and customer reviews. This method is developed on a data set that was a public data set from Airbnb listings of New York City. So as for the contributions of this paper was the first time that average customer sentiments were extracted from raw reviews of each listing on Airbnb, and it was used as a feature for creating the predictive model for the listings. Also, this was the first time that neural networks were used to predict the prices of Airbnb properties. Now let's jump into the dataset that we've used and the pre-processing that we did on the data. The dataset, as I mentioned, was a public Airbnb dataset for New York City. The data included 50,000 rows with 96 features each on owner information and property characteristics. That included number of rooms, bathrooms, coordinates of listing, and so on. The label that we used here was the natural log of the price per night of the listing in US dollars. This figure here shows the spread and the massiveness of the data that we had used. This shows each point corresponds to a single row in the data set that we have used, or a single listing in the Airbnb listings of New York City. So for the pre-processing, we looked at the raw data, which included 96 features, which had categorical data and NA values. For removing we removed the NA values, and for the categorical features, we converted them into one-hot vectors to be manipulatable by our models. The sentiment analysis that we did on the raw text using text blob converted them into average sentiment values for each listing that was averaging all the sentiment scores for each of the listings and assigning that as a new feature for each of those listings. Finally, we got to 764 features, which we split the data set into 40,000 training examples, 5,000 validation, and 5,000 test examples. Now let's dive into the feature importance analysis that we did before training the models. We tried a number of methods. First one was manual feature selection. Second one was p-value feature analysis. And the third one was using lasso cross-validation feature importance analysis. As you can see, the R-squared score of linear regression with each of these features is shown in this figure, and the lasso CV had a pretty good R-squared score with this method. After doing the lasso CV, we got 78 features for using the machine learning models and building them. Now let's get to the machine learning models that we use in this paper. The first model that we used, or the baseline, was the linear regression with the entire feature set. And then using the selected features using lasso CV, we used ridge regression, which is basically linear regression with L2 regularization. We use k-means clustering and ridge regression, which was what we did here was that we used k-means clustering to cluster the data points into several clusters and then apply ridge regression to each cluster. The reason we did that was to capture the nonlinearity in the data better, but still use a linear model as the ridge regression. Then we used support vector regression with RBF-kernel. This enabled us to capture nonlinearities and the nonlinear correlations between the covariates in our data set. Finally, we use a fully connected neural network with 2 hidden layers and ReLU activation function in the hidden layers and a linear activation function in the output layer. We also use gradient boosting tree ensembles to try to capture more the nonlinear relationship between the output or the label and the input features. As for the evaluation metrics to see how our models were doing, we use mean absolute error, mean squared error, and the R-squared score of predicted versus actual labors, which again were the natural log of the prices. Now let's get to the results that we got using these machine learning models. So what you see here are the performance metrics of the trained models sorted from smallest to the largest value of R-squared score on the test split. You can see that linear regression or the baseline model had a very small R-squared score on the test split, but a much larger value on the trained split. This shows that it was overfitting badly. So we expected that with the reduced number of features and with the feature importance analysis, we would get better models. And you can see that that is the case. So basically, LassoCB improved the baseline of this R-squared score for most of the models that we tried here, such that the minimum value we got for gradient boosting was around 59%. So the top 3 models in terms of R-squared score were neural network, k-means plus ridge regression, and the support vector regression. However, still you can see that the neural network specifically has overfitted the data. And the reason we expect that to be that the number of features were too large compared to the training data set and the number of epochs that we trained the neural net on the data. So what you saw here was that we tried to design a model for predicting the Airbnb prices for the listings in New York City. And this could be used by the owners as well as the tenants. We tested several machine learning models, and the best models that performed for us were the k-means and ridge, also SVR, and the neural network. We also saw that the feature importance analysis was a very important part of the process because it majorly boosted the performance of all models regardless of what we had used. Also, a point that's worthy of mentioning is that the k-means plus ridge and the neural network suffer from high variance. K-means and ridge suffered because some of the clusters that are made by k-means had too few number of training examples for the ridge to be to not overfit the data. Same for the neural net. Finally, given the heterogeneity of the data set and the simple approaches we use here, a 69% R-squared score for the best performing model, that was the support vector regression, seems pretty good. As for the future works, we expect that trying other feature selection methods such as random forest and correlation-based feature selection would give us good improvements on the existing models. Also, experimenting with the neural net architecture and using other machine learning models would definitely help explore this problem more deeply. Using regularization techniques are specifically important here, as we saw some models were overfitting the data. Also, we can get more training examples from other hospitality services, or maybe even Airbnb data sets from cities close to New York City or any other cities that will be expected in future works. This would help reduce the variance of the models. And finally, improving the sentiment analysis by perhaps including other metrics than the average sentiment score for each listing would definitely be helpful in creating a better feature from the reviews for doing the prediction. Thank you very much for your attention. Please check out our paper for further details, and you can find in this link the repository of this research.